Hey guys, so for those of you who don't know me, hi, my name is Oscar Sabalainen. I do a lot of AI stuff, particularly a lot of neural network quantization stuff, and today's video is going to be about GPTQ. It's an extremely common quantization technique, post-training quantization technique, particularly with large language models, LLMs. It's one of the more common ones. There are other ones that quantization is a pretty fast moving space, things that come out every year. AWQ is another one. But today's video is going to be about GPTQ, and my objective for today's video, it's going to be a little bit long, but I basically want to go through the GPTQ paper and explain it from scratch. Like, I'm not going to dive into every single little detail because some of these things are a little bit removed. In my opinion, maybe you need to know them, maybe you don't, but some of, in general, the big picture stuff that's everything that is basically going to overlap with a lot of other useful things in machine learning that are useful to understand, like, optimization theory when it comes to Hessians, GPUs and compute bound versus memory bound. All of these things I'm going to go into more detail on, but then little bit itty bitty details I'll probably skip. Anyway, with that kind of intro aside, let's get into GPTQ. If you want to understand it, hopefully this is the video for you. I haven't seen anyone else really explain GPTQ from scratch. And that's because there's really a lot to it. This touches on many different areas of machine learning, so I think it's good as a general introduction to a lot of stuff. But I think you'll probably learn something from this video. I'll try to keep it as brief as possible. With that note, let's get into it. Okay, so first thing for understanding GPTQ is that we're going to start off with a scenario. You're a machine learning engineer, you've been given an LLM, but it's too slow. It's all in floating point, and you're going to reach for one of the most popular techniques for speeding up neural networks, which is quantization. Because you're in LLM land, and the only thing that you really need quantization for is to speed up inference, you're not held hostage to the other things that quantization might be used for, like making sure it only runs on CPU, or even things like determinism. You're really just mainly concerned about running on a GPU. You want to make it run more quickly. And we'll talk more about GPU, optimization later. But the main reason people use quantization is to make the weight tensors smaller so that you can load them onto whatever part of the GPU they need to be on more quickly, so just less data moving around. And then when you're actually doing the calculation, often you cast it back to floating point and you do the calculation in floating point space, but it's all about just making the weight tensor smaller. So you're doing quantization in that space. And because you're doing quantization in that space, and that's the only thing you're using quantization for, you're happy to do row by row quantization. You could do tensor level quantization if you wanted to, but the problem with tensor level quantization is that you have one set of quantization parameters for your entire weight tensor, and that doesn't give you the best level of granularity that you could if you did it on a per channel basis, which is standard, or you could even go further and you could do it on a per row basis. And the benefit of doing it on a per row basis is that suddenly you're getting pretty much as high granularity for your quantization as possible. It doesn't mean you need more quantization parameters, but maybe you're okay with that. Maybe you're okay, you're willing to sacrifice the fact that you need an extra tuple of parameters for each row if that gives you that much better quantization granularity and a reduced quantization error. As you can tell in this video, I'm not going to go into the basics of quantization. If you are interested in the basics of quantization, I have a video here where, 20-minute introduction, basically a lot of stuff for quantization. But yeah, as I said, you're in quantization land, you're happy to do row by row quantization, or even group level quantization. You can treat groups of channels as blocks. You take 5 channels, you treat them as a group, or 200 channels, whatever. But anyway, that's the setting. You're doing LLM quantization, and you're doing row by row quantization. And this is your task. Now, in this scenario, you are a particularly ambitious machine learning engineer. You could do the simple thing, which is just pick quantization parameters for each row naively, use a min-max observer or a mean squared error observer, whatever observer, and do it that way. But you have decided that no, you're gonna make your mark, you're gonna do something clever. And so the idea that you've come up with is that you're gonna quantize a row, And then you're gonna, and you know that every row that you quantize, that's gonna introduce some quantization error. It's gonna slightly impact the output of your layer, potentially in a negative way. And so what you've decided to do is that you're gonna quantize one layer, and you're gonna try update all of the remaining floating point weights so that the final output of your layer is as close as possible to the original floating point output. You're basically gonna quantize something, and then you're going to adjust everything else to try and compensate for the thing that you just quantized. Then you're going to quantize another row and another and keep going. Now this is ambitious, but that is the point of GPTQ. And don't worry, this didn't just drop out of the sky in one paper. There was a long history to this, and in this video we're going to go over some of that long history because it's useful for understanding particularly like the mathematical side of GPTQ and how we come to these things. So to understand how this kind of came about, there's three main papers that we need to look at. One is Optimal Brain Surgeon, which is, it basically came up with this idea, but just in the context of pruning, where, for those of you who don't know, when you prune, you basically just remove certain rows from a tensor. You want to make the tensor smaller, you want to make your model smaller, you decide that, hey, maybe we can just set the weights to equal to 0, and you do so, and when those weights get set equal to 0, you can just remove them from the tensor, and then that kind of speeds up your general operation. And so they developed this in the context of pruning, and then optimal brain compression came along, and it generalized this to also include quantization, which is similar. And then GPTQ came along, and then GPTQ, its main contribution was computational optimization, because the techniques from OBS and OBC, they were great, but very slow. Like, if you had a big model, this could take hours, days to operate on, versus GPTQ, they're able to take one of these large language models and quantize it in minutes. In a couple of minutes. So it's all about speeding up, and by like even up to 3 orders of magnitude speed up. So very good. So, okay, how do we, going back to the question, like how do we figure out which row to pick and how to update the floating point weights? Well, the general procedure for this is that we're going to take a layer, like most post-training quantization techniques, we're going to feed some calibration data through it. And then what we're going to do is we're going to measure the quantization error, also standard. In this case, we're going to use mean squared error for quantization. We're going to look at the mean squared error between the floating point and the quantized tensor. That's going to go by quantization error. And then what we're going to do is that, and this goes back to OBS, what we're going to do is we're going to pick the row that minimizes the quantization error. So we're going to pick the row that is easiest to quantize, and then the last step, update the floating point weights. And we're going to do that using the Hessian matrix. So if we look at the GPTQ paper, we can see that this is the equation that they give for the mean squared error. If you're familiar with this kind of math, it should be fairly simple. We can see that, you know, Wx is just the forward equation, and then W hat x is for the quantized layer. So Wx is floating point, W hat is quantized. And the rest of it just mean squared error. And I will say that in the GPTQ paper, they've made a small mistake, which is that they say that this is the kind of Wx is the forward call for a linear layer, when that is not true. It is for a convolutional layer. And the reason this came about, I think, is fairly simple. It's just in the OBS paper, it originally talked about convolutional layers, and it had this equation, and then it carried it over. And I think it's just been a mistake. So for convolutional layers, it is Wx, and that mean squared error equation would be correct. However, for linear layers, it is xw. Now, there is a consequence to the fact that these equations are different, and that is that the Hessian equation that they give in the paper is also incorrect. For convolutional layers, it is 2xx transpose, like they say in the paper. But for linear layers, it is actually 2x transpose x, which is different. Now, the thing that we really care about is that, okay, is it correct in the code? And I have looked in 2 separate places for the GPTQ algorithm. One is the code that the original code that the authors wrote, and the code is correct. They, if they're dealing with a linear layer, they just add an extra transpose to x, the input, and it all comes to the same, so the code is correct. And then also I looked at the PyTorch implementation of GPTQ in Torch.io, and Torch.io is a fantastic library, but I'm not talking about that in this video. And there they also have the correct equation for the Hessian. So we don't need to worry, all of the code is correct. As far as I know, everything else in the paper is correct. It was just, there was this one small mistake that I wanted to mention just because it drove me nuts when I was originally going through the maths of this. I was like, I couldn't get the Hessian to come out right, and I was like, what's going wrong? And then I realized the equation in the paper is just wrong, so I thought I'd highlight it. From there, we have these two equations. One is, this tells us which row we're going to pick to quantize, and then delta F is going to tell us how we update the remaining floating point weights, so as to try and minimize the quantization error. This looks like a bit of a mouthful, but we're going to go over it bit by bit. But first, we're going to talk about what is the Hessian matrix, because I think it's useful general context. So the Hessian matrix is basically a matrix of second-order derivatives of a function, in this case, our mean squared error. And we can think of this in terms of probably the easiest way to understand why this is even useful, or kind of gain an intuition around using this, is looking at one of the OG optimization methods, which is Newton-Raphson method. So in this scenario, we have an arbitrary loss function, we have a loss landscape, and we are trying to find the local minima or the global minima of a function. Yeah, we're trying to minimize this function. And we have a loss landscape detailing this. There's peaks, there's valleys, but we're trying to get to the bottom of it. And there's two main techniques that can be used for this. There's grid search, which is just brute force it, look at every single possible parameter combination at some resolution, and try and just pick the one that has the minima. People don't tend to do that because it's extremely computationally expensive. If you have billions of parameters, it's a no-go. Even if you have thousands, it's very expensive to do. And so, because there's just this massive explosion combinatorial issue, you can't do it, basically. So what people do instead, we use optimization techniques. And the idea here is that no matter where you are in the loss landscape, your optimizer should be able to find its way to maybe not a global minima, but at least a local minima. So no matter where you are, by incrementally taking small steps, it's going to find the solution to your problem. And gradient descent is the classic technique that we use for neural networks in this scenario. And so if we're looking at the Newton-Raphson method, for example, and this is where Talyor series become useful, is that when you are at a specific point, I'll explain Talyor series, because Talyor series are a very interesting object and extremely useful in this scenario, in that it turns out that no matter where you are, as long as your function is, you can get the derivatives of it, the higher order derivatives of it, if it's all smooth, then it turns out that you can actually estimate your entire loss landscape from wherever your model parameters are using just the derivatives, the higher order derivatives of your function in what's called the Talyor series. So it's extremely useful just by taking the derivative, the second order, third order, fourth order, and it's a Talyor series. The more orders of derivatives that you add to this, the better that your estimation of the overall loss landscape, not even locally, but like beyond where you are locally, the more elements that you add to this, the better your estimation is going to be. And so to gain kind of an intuition for this, imagine we're at some arbitrary part of the loss landscape and we take the first order derivative. The first order derivative is also called the gradient or the slope, and that doesn't tell us very much. It basically just tells us what direction we want to step in to get to go down. Basically, we're on a hill, it tells us downhill is that way, take a step that way. But it doesn't tell us how big of a step we should take, because if we're just treating the first order derivative as our entire estimation of the loss landscape, that would mean that you should just take an infinite step in that direction. You know, downhill is that way, take as big of a step, take an infinitely large step, and you'll end up downhill. We know that that's not true, because we know that our first order approximation is probably not a good estimation of the loss landscape, and probably what we're going to want to do is get a bit more information and know how big of a step we should take, because going infinitely in a direction, probably not a good idea. So what we do is, well, for this Talyor series, what if we just add a second term? And the second term is the Hessian. And so if we say that the first order derivative gives an idea of the slope, the second order derivative gives an idea of the curvature. It tells us roughly, what the curvature is like at that local point of the loss landscape, wherever we are. And so if our first order Talyor series was a linear equation, now our second order is a quadratic. And the quadratic has a minima because it's a curve. And that tells us it might not be a very good approximation of our loss landscape, but at least it has something practical we can aim towards. We know that, okay, we don't want to take an infinitely large step. There's some finite level of step that we want to take. And for those of you who have trained neural networks, I mean, probably you have if you're watching this video, but yeah, you're familiar with the concept of learning rates, right? And learning rate tells you like you take a step in that direction. Yeah, how big of a step is dependent on this Hessian. Now, typically neural network optimizers, often they don't just actually calculate the Hessian, they calculate like approximations of the Hessians or using some sort of heuristic, because Hessians can be expensive to calculate. But yeah, that's the basic idea. That's why we like Hessians. So going back to these original equations, okay, we understand what h here. H is the Hessian and h minus 1 is the inverse Hessian, but still that doesn't give us a lot of context to understanding these equations. So I think a better understanding is if we go to the Optimal Brain Surgeon paper. This will actually give a bit better understanding. It won't give a complete understanding because Optimal Brain Surgeon is about pruning instead of quantization, but I'll try to update its quantization on the fly. If you're really interested in this, I highly recommend reading both the Optimal Brain Surgeon and the Optimal Brain Compression paper, because Optimal Brain Compression goes more into quantization. But the explanation here is very good, so I'll stick with this one. So the first assumption that they make is that, and this is again is for pruning, so they consider that the network's been trained to a local minima in error. What that basically means is that you've been training and now your loss is about as low as it's going to go. In the case of quantization, that's fine, that's always true. If your loss is your quantization error, then your floating point network is always at the local minima in terms of quantization error, because it's a purely floating point model. So it's always as well quantized as it can be, being a floating point model. So yeah, this condition is also met by quantization. So the second step is that they say, okay, we're going to take this Talyor series expansion of the loss, like I mentioned earlier, is that they have their first order element, which is given by here, and then the second order, which depends on the Hessian, and then this third order component. And what they say is that because they've trained to the local minima in error, that means that the first order derivative is actually 0. It's flat because they're at the bottom of this kind of valley. You can't go up, you can't go down, you're where you should be. And so they throw that term away, they say that's equal to 0. For the case of simplicity, they ignore the third and all higher order terms. And so basically the entire estimate of the loss is this second order component of the Hessian. Cool, so that's great, that's already simplified things. And then if we say that in the case of pruning, they're just trying to set their row to 0, essentially, and so they add the opposite of whatever the kind of weights are for that row, and then they generalize it in unit vector space, and then they're just trying to solve this problem. They're trying to minimize the loss while setting some row to equal 0. And from that, they form a Lagrangian, and from that, they split it up, functional derivatives, matrix inversion, to find these so that they know what updates they should do and then what row they should pick to prune. In the case of quantization, slightly different, because you're not limited to adding a value so that everything equals 0. In other words, you don't just have one target that you're aiming for, you have up to 2 to the power of whatever your number of bits is. If you're doing 8-bit quantization, then you have 256 possible targets that you're aiming for. You're basically just trying to snap your floating point weights onto the quantization grid rather than just set them all to 0. So it's slightly different, but the concept is there. Then, okay, so that's where these equations come from. Again, slightly different for quantization. I recommend looking at the OBC paper if you're interested, but that's the basic idea. Then once you've done that, okay, you've picked your first row to quantize and you've updated your floating point weights. Now you can remove that quantized row from the rest of the optimization problem because you've already quantized it, you're good. You don't need to think about it anymore. That is as simple in the equations as just removing that row and that column from the Hessian. In practice, you don't want to do it that way because what you really need from the Hessian is the inverse Hessian, and calculating inverses is quite expensive, especially if these things are like, you know, if there's very many parameters involved in this, even 1,000 parameters is going to be 1,000 by 1,000. This thing's going to be expensive to calculate the inverse of. So what you can do is that you can use a step of what's called Gaussian elimination. Gaussian elimination is it's a technique for solving systems of linear equations, and yeah, you can just apply it in this case to solve to basically remove the contribution of that row / column from the inverse Hessian directly in the inverse Hessian space. So you don't have to recalculate the inverse Hessian, you just have the original inverse Hessian, you apply one step of Gaussian elimination, and it's kind of cool. And you can just remove that row and that column from that matrix. Okay, cool. That is basically all we need to know about the mathematical side of GPTQ. So, welcome, quite dense, but hopefully that was useful or interesting. And now we're going to talk about what the actual contributions of GPTQ are in terms of computational speedups. So the first thing is that GPTQ made this observation, and it was that, going back to the original idea about, we're going to pick which row to quantize based on whatever minimizes the mean squared error, well, the GPTQ authors were like, what if we don't want to do it that way? What if the problem with doing it in this greedy data-driven approach is that at the end of the day, or at the end of the tensor rather, the last rows that you have to quantize, they're by definition the rows that are most difficult to quantize, and then you don't have very many, if any, floating point weights that you can adjust to compensate for the quantization error. So you might just be tail loading your entire quantization error. And so their argument was like, what if you just did all of this in a fixed order? What if you didn't try to be fancy about it? You still updated all of your floating point weights every time you quantized the row, and you quantize rows sequentially, and then you updated the remaining weights. But what if you just did it in a fixed order? What kind of optimizations could that unlock? And that was the contribution of GPTQ, and that's what allowed them to speed things up by like 3 orders of magnitude. So the first optimization is suddenly when you're quantizing a row and you're using your inverse Hessian for that, the only contributors to that inverse Hessian are the floating point weights. You no longer have the contributions of all of the quantized weights. And so if you know for each row what is the set of floating point weights that's going to contribute to its inverse Hessian, and you know this beforehand, before you quantize anything to begin with, then suddenly you can pre-compute all of this. And pre-computing it turns out to just be massively faster. I didn't understand the explanation they gave in the paper. They said that just because you pre-compute it, suddenly it means you can do less computation, that somehow you do less steps of Gaussian elimination. I'll take their word for it. The kind of assumption I have about why it would be so much faster is that, one, on the GPU side of things, it allows you to know that for each row that you're quantizing, you're not waiting for the step of Gaussian elimination. You know that it's all been done and then it's just loaded to where it needs to be. And it allows you on a GPU side to figure out the compilation that much more efficiently. And then if calculating the inverses wasn't a computationally expensive thing to do, you could just turn what is a sequential problem into a parallel problem and solve all of these independently. But this question about why it's faster to do Gaussian elimination comes back a bit later, so we'll come back to this later. But for now, suffice to say, when you can pre-calculate all of these things and everything is in a fixed order, that speeds up your computation. So that's one thing. But the second thing that they noticed is that while they're doing all of this quantization on a GPU, that they're running into memory-bound issues, which is kind of a classic problem with GPUs. So in GPUs, and typically when we talk about compute, there's a few different terms that we use in terms of what's the bottleneck. What is the thing that's actually slowing down the computation significantly? And we can talk about something being compute bound, and that basically means that just the computation that you're doing is the thing that's slowing you down. Once you get the numbers and you're crunching them, that's actually the slow thing. Memory bound means that getting the data from memory, that's the thing that's slowing you down the most. Input-output bound means that basically sending the data to the CPU/GPU and sending it away, that's what's taking the most amount of time. So an analogy that I was thinking about using for this video is that imagine you work in a big bureaucracy and you have your cubicle, you have your office, whatever. Compute bound would be that you writing and filling in all of the forms, that's what's taking the most amount of time. That's the actual bottleneck. If you could write faster, if you could check boxes faster, then that would be good, and then everything else would speed up because that's the bottleneck. Memory bound would be that basically it's internally getting access to all of the forms that you need. The form that you need, it's in the other department, which is in the other building. You have to walk over there, you have to get it, you have to bring it back. that's what we would consider memory bound. A lot of messages flying over the place, and the time that it takes for those things to move around is what is like the slow thing. Input output bound could be that like the bureaucracy is in a building, the building is in the middle of the desert, it's far away. Every time someone wants a decision, they have to like send, a form there, they have to get it back. The internet doesn't exist, they have to do it manually, and it takes them like 5 hours to do each time. Even if inside the bureaucracy everything was blazingly fast, input output bound would be like it's actually getting there and back, which is like the slow thing. In the case of GPUs, and particularly large language models, things tend to be memory bound. It's moving the data around that is actually the heavy part. Doing the compute, the GPUs are blazingly fast these days. It's really moving the data around. That's what a lot of like CUDA kernels and like CUDA optimization comes down to, and generally GPU optimization comes down to trying to solve for this memory bound environment that we're typically in, especially with LLMs. And in certain cases they can be like what's power bound, but that's like a little niche. I'll actually put a link for power bound GPUs in the description just because it's interesting to read about. But yeah, because, and like I mentioned earlier, the reason we do quantization with LLMs is because we're memory bound, because it's the size of the weight tensor that we're trying to minimize. We're trying to minimize the amount of data that we send around. So the authors of GPTQ, they realized that in order to speed all of this up, what they could do is that they could use a classic technique from GPU optimization, which is lazy batch updates. You basically only update, because on the GPU, everything being parallel, there's often copies of a weight tensor all over the place and they're doing kind of different things. You only need to update those copies when you need to update those copies. You don't necessarily need to update them every time they get updated locally. So the kind of analogy here, if we go back to our bureaucracy, is that you have a bunch of work to do and it requires you to have access to 50 different forms. You have to check this, check that, check this. You have to look at a bunch of different things in order to compile your report, let's say. And you could live in a situation where someone's coming over to your cubicle or your office every minute and handing you another piece of paper. You have to get up, you have to say, hi, how are you doing? You have to take it, you have to put it back down, go back to doing some work. And this keeps happening every minute for 50 minutes. And a more optimal way of doing it is probably no one brings you anything until the 50-minute mark, and then they just bring it all to you in one go. You say hi, thank you, how's your day? And then you take it and then you go back to doing your work. And then you can do it all in one go and it's all much more efficient. And as a result, in the building, in the bureaucracy, people aren't whizzing around with individual pieces of paper. People aren't now bumping into each other because, it's just occasionally a person walks and gives like a handful of files all on one go, and everything just works better. That's basically what they did with the lazy batch updates in the GPU. And really, going back to like the quantizations instead of this tortured analogy, what they did is that they, when you're quantizing a row, the only things that you really need are one, the inverse Hessian, which has been pre-calculated for that row. So you have that available, that could get loaded whenever you needed it. And then also the rest of the weight tensor. Now, in particular, your weight tensor needs to be up to date when you're quantizing a row. All of the adjustments to the floating point weight, you have to have those. The quantized weight, you can ignore the quantized weights, they don't really matter, but the floating point weight update, you need to have those. But you only need them when you're quantizing that row. It's only once you need it in like a lazy sense. Once you need it is when you need it. Before you need it, you don't need it. And so the basic idea of lazy batch updates is that they'll take a chunk of rows, let's say 200 rows, 256 rows, and they'll quantize all of those sequentially. So they'll, update the floating point weights, quantize a row, update floating point weights, quantize a row. And then only once they're done with that batch, then they send it out to all of the other different parts of the GPU. And that is how they solved helped solve the memory bound issue. Came with significant speed ups, and the GPU was able to quantize this entire thing faster. Sounds silly, but it works. And then finally, the last actual optimization that they did for GPTQ is going back to this question of Gaussian elimination. I mentioned earlier that the Hessian is a symmetric matrix, and it is also what's called a positive definite matrix. And generally for all of these, the problem that we're looking at, which is quantization, that will always be the case. Because this is all kind of like smooth and, we don't need to worry about it. Basically, that's always going to be true. Now, a problem that they were having with the Gaussian elimination, particularly with batch updates, is that they were running into numerical instability issues. You can imagine, and for those of you who don't know, numerical instability, it's typically when you're dividing by a very small number that's close to 0, things blow up. The numbers stop working, particularly in floating point space. You can end up having very large numbers in places. Things don't really scale well. And it can lead to basically your entire program crashing if like a number goes out of bounds or something. And so the classic technique to solve this is using dampening. It's kind of cheating, but like you can just add a small value, like an epsilon value, to whatever near 0 value that you have, and that kind of helps solve the stability issue. They tried that. They said that it worked for small models, not so much for big models, maybe because you have to do more steps of Gaussian elimination, and so that dampening factor wasn't as efficient. But they kept the dampening factor, but then they also tried something else, which is that they just got rid of Gaussian elimination entirely, and what they used instead was Cholesky decomposition. And because Cholesky decomposition is another way of solving systems of linear equations, is just you can only use it in specific circumstances, like if a matrix is symmetrical, positive, definite, like our lovely Hessian matrix. And particularly, it just comes out really nicely when you have everything in a fixed order, because the Cholesky decomposition, it being another way to solve linear equations, but one, it's faster, and two, it doesn't have numerical instabilities. But the output of it is just so beautiful and so intuitive, because it ends up just being an upper triangular matrix where you can just see for each row that you're quantizing what are the contributions of the floating point weight to the inverse Hessian. So in the first row, because it's an upper triangle matrix, everything contributes. In the second row, everything except the first row contribute, because everything else is set to, the lower left triangle is set to 0. So it's kind of like a beautiful intuitive observation of the inverse Hessian contribution. But all that to say, that's also twice as fast than Gaussian elimination, because it has half as many floating point operations, because it has this assumption of symmetrical matrix built into it. And there's also been state-of-the-art Cholesky kernels. People have been working on these for a long time, so they're very optimized, so they're really fast. And again, numerically stable. So all that together is what made GPTQ, compared to OBS, compared to OBC, their contribution was a fixed order of quantizing all of your rows in. You can do this in a group-wise fashion or a row-wise fashion, and then pre-computing the Hessians using Cholesky decomposition. And then the final contribution was the lazy batch update. Altogether, that gives you up to 3 orders of magnitude of speedup, which is crazy, but it goes to show that like little things can get you a long way. But when it comes to GPU, it's important to understand your environment and where you're working, so you're not doing like silly things. And then I'm not going to go into the results section of this paper, just because you can assume if everyone uses GPTQ that it's pretty good. It's not in theory or in practice as good as things like even like OBC, like in its raw form, or things, I'm actually blanking on the name right now. I'm completely blanking on the name of a technique that I'm thinking on. I'll say other gradient descent methods like QAT or something, whatever. There's a specific technique I'm thinking about, but I'm completely forgetting what its name is. Oh no, it's this, he added in post-editing. But yeah, that was it. Hopefully this video was interesting / informative for you. I can only apologize if I belabored certain points that you're already familiar with, like Hessians or GPU computation bound issues. But yeah, I wanted to cover all of that because I think the GPTQ paper, it's really good because it touches on so many different parts of machine learning that if you understand it, I feel like that, yeah, it helps you understand a lot of different parts of machine learning. So anyway, that was it. You know, as always, I'll make other videos on quantization. I'll probably make videos on other stuff as well. There's some other little Python related things that I wanted to make videos on. But that was it for this video. If you have any questions about quantization or machine learning in general, please reach out, leave a comment or whatever. I'm always happy to help. If you like this, press a like. If you want to subscribe, I appreciate it. And yeah, see you next time. Bye guys.